Hey everyone, I'm Kramer, and at the end of this video, you'll be an expert at using 2's complement. 2's complement method is one of the most common and efficient ways to represent signed numbers using binary digits. And by sign, we just mean numbers with a sign in the front, so either a positive or a negative sign. So basically, 2's complement allows us to store both positive and negative values in binary. In this method, we reserve the leftmost bit, also known as the most significant bit, to indicate the sign of the number. 0 for positive numbers and 1 for negative numbers. So simply looking at these two binary numbers, we can easily tell which one is negative and which one is positive. For n bits, the sign bit has a weight of negative 2 to the power of n minus 1. So if we have 8 bits, the leftmost bit has a weight of negative 2 to the power of 7, which is negative 128. When this leftmost bit is active, it switches the number to negative. So negative 128 is the lowest negative number we can store in an 8-bit binary number using 2's complement, and that would look like this. So we have a 1 on the leftmost bit, and the rest of the bits are set to 0, meaning the leftmost bit is on and the rest are off. Adding up all the on bits, we get the value of negative 128. For the highest negative number, we activate all the numbers like this, so every bit is set to 1, and adding up all these active numbers, which is all of them, we get negative 1, the highest negative number. So yeah, it's pretty neat how having that significant bit represent a negative number can produce all these negative values. Let's quickly also compare this to non-negative numbers. For the lowest non-negative number, we set all the bits to 0, which when we add up all the active numbers, there's none of them, so that value is 0. The highest non-negative number we can get is we set all the bits to 1 besides the leftmost bit, which remains as 0. Adding up all these active bits gives us 127. Knowing the size or number of bits you are using to represent the binary number is essential when working with 2's complement. We need to have this number at the correct size for accurate representation and correct operations. Remember also that the most significant bit needs to be in the correct place. You will most likely see sizes of 8, 16, or 32 bits. Having n bits gives us 2 to the power of n possible representations, but half are positive and half are negative. For example, with 8 bits, we have 2 to the power of 8, which is 256 possible combinations, but only 2 to the power of 7, which is 128 distinct positive values that can be represented in 2's complement, ranging from 0 to 127. The other half of the range is allocated for the negative values, spanning from negative 128 to negative 1. So when actually performing 2's complement to find the representation of a negative number, we first start with the binary number of the absolute value. So say we want to represent negative 20 with 2's complement. First we get the binary value of 20, and then perform the following 2 steps. Step 1, 1's complement, which involves flipping all the bits. And part 2, we simply add 1 to the rightmost bit of the 1's complement result. So let's take a quick look at 1's complement. All we are doing is simply flipping all the bits in the binary number. So all the 1's become 0s, and all the 0s become 1's. A little example here, we've got 20, the binary number is 0001, 0100. To get that negative representation of negative 20, we simply flip all the bits. So all the 0s become 1's, and all the 1's become 0. And our result is 1, 1, 1, 0, 1, 0, 1, 1. And that would be negative 20 in binary, using 1's complement. Another quick example, we have 42. Same thing, flip all the 0s to 1's and 1's to 0s, and we've got negative 42 in 1's complement. So the difference between 1's complement and 2's complement is we add a 1 to the result. And I'll explain why later, but let's have a go at it now. And just remember, these are the addition rules for adding binary numbers. When working with binary numbers, 0 plus 0 equals 0, 1 plus 0 equals 1, 1 plus 1 equals 1, 0, so we write the 0 and carry 1 to the next place value. Okay, so back to our previous 1's complement result for 20, and let's add the 1 to the rightmost bit. 1 plus 1 is 1, 0, we write down the 0 and carry the 1. Now continuing, we got the same, 1 plus 1, so we write down the 0, carry the 1, and now we got 1 plus 0. So that results in 1. Now fill in the rest of the number, and this is our result. And that's it. This is minus 20 in 2's complement form. Okay, so say you get a question, convert decimal number -42 to an 8 bits 2 complements representation. Here's the easiest steps for you to follow. 1. Find the binary value of the absolute value, so 42. 2. Pad, if needed, to 8 bits. 3. Perform 2's complement. Okay, so now let's do this on paper. So we're looking for, the question's asking for -42, but the first step, we want to find the binary number of the absolute number of -42. So that's 42. So to find the binary number of 42, what we want to do is use the divide by 2 method that I went over in the previous video. So 42 divided by 2 equals 21, remainder of 0. 21 divided 2 equals 10, remainder 1. So I'm going to keep building up these remainders on the left hand side, and that's what's going to build up my binary number for 42. So 10 divided 2 equals 5, remainder 0. 5 divided 2 equals 2, remainder 1. 2 divided 2 equals 1, remainder 0. 1 divided 2 equals 0, remainder 1. And we stop here because we have reached a result of 0. Okay, so now I read my remainders from bottom to top. So going this way, so my resulting binary number is 1, 0, 1, 0, 1, 0. Okay, so this would be my binary number representation of 42, and this is fine, but the question asks for an 8-bit number. So what I need to do is pad the number to the correct number of places. So to pad the number, what I do is I need to add to the left-hand side zeros. So to get from 6 to 8, I'm just going to add 2 zeros to the left-hand side of the number. And now I have my 8-bit binary number representation of 42. Why this is important is mostly because of this significant value. When we do 2's complement, this significant digit needs to be in the correct place because this is what's controlling if it's negative or a positive. So we do need the 0 and 1 to be in the correct place at the left-hand side. Okay, so now I'm going to continue doing, so now we got 42, but we want to find the binary value of -42. So to do this, I'm going to continue with 2's complement, and the first part is to flip all the bits. So with my number 0, 0, 1, 0, 1, 0, 1, 0, and I'm going to flip all the bits. So change all the zeros to ones and all the ones to zeros. So this number becomes 1, 0, 1, 0, 1, 0, 1, 1. Okay, and that's the first bit done. Now I do the second part where I add 1 bit. So I add 1 bit to the right hand side. Okay, so with my number 1, 1, 0, 1, 0, 1, 0, 1, and I'm going to add 1 to the right hand side. So if you remember, 1 plus 1 gives us 1, 0. So put down the 0, carry the 1, and I'll have 1 plus 0. 1 plus 0 is 1. And then we're done here. We just fill out the rest of the number. Okay, cool. And now this is my answer. So we've finished 2's complement, and my answer is now 1, 1, 0, 1, 0, 1, 1, 0. And that is the negative binary representation of -42. And that is the binary representation of -42 using 2's complement method. Cool. Okay, let's do another example using -69. And we want to find the 2's complement binary representation of -69. So to do that, first, we want to find the binary representation of the absolute value of -69, so 69. Again, doing the divide by 2 method. Okay, and so we stop again because we got to 0. And read our binary number going this way. So 1, 0, 0, 0, 1, 0, 1. Okay, count our numbers 1, 2, 3, 4, 5, 6, 7. We got 7, and we'll just pad it by 1 on the left hand side. Okay, and now starting to do 2's complement, we flip all the bytes, all the bits. Flip all the bits, so 0, 1, 0, 0, 0, 1, 0, 1. And flipping that, we get 0, 1, 0, 1, 1, 1, 0, 1. Okay, and now we just add 1 to the right hand side. Okay, so 1, 0, 1, 1, 1, 0, 1, 0, plus 1. And that will just give us 1, 0, 1, 1, 0, 1, 1. And so that would be our binary representation of negative 69 using 2's complement. Okay, so just another way we could have solved this is by using a table. And how that works with binary numbers, they're all powers of 2's. And so what we can do, we know it's an 8-bit binary number, as the question asked. We can create a table that's 8 bits long. So we'll be going from 2 to the power of 0 to 2 to the power of 7. So if I just create that as a table, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. I made it a bit big, but it's alright. And just above this, I'm going to just solve the powers. That just makes it a bit easier. So 2 to the power of 1 is 1. Sorry, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 16, 32, 64. And with this last one, because we're using 2's complement, the most significant power, it should be negative. So this should be actually 2 to the power of negative 2 to the power of 7. Why this is, this allows us to have negative or positive numbers. So if a 1 is placed here, we know our number's negative. If a 0 is placed there, we know it's a positive. Yep. And so now what I'm going to be doing is above this is placing the 1s and 0s. We've got eight spots, and starting to build up a number that brings us to negative 42. And because it's negative 42, straight away, because it's negative, we can place a 1 here at negative 128. And what makes things easier, just start building up our number on the side. So we've got negative 128. The next possible number we can put in is, 64. So positive 64. So now we have negative 128 plus 64. That would give us negative 64. Okay, now I'm looking for the next number I can put in. The highest next number that doesn't put us underneath 42. because I need to get to 42. So 32 wouldn't be good because that's going to take me lower than 42. So it's going to be 16. Put the 1 on 16. So negative 64 plus 16. That gives me negative 48. So looking for the next highest number that can go into 42. Finding the next number that's going to get me closer to negative 42. So it can't be 8, that's going to take me too low. So it has to be 4. 4 will take me down to negative 44. And so then the next number I can put in is 2. 2 matches perfectly, so I can stop there. So plus 2 equals negative 42. And I can fill in the rest with zeros, and this gives me my 2's complement binary number representation for negative 42. That's 8 bits long. So the number is 1, 1, 0, 1, 0, 1, 1, 0. And you'll see that's the same number, same result that we got before with the other method. Okay, so I'm just doing another example with a positive value to just see how it's different. The most significant power is a negative power, so negative 2 to the power 7 gives you negative 128. And then what that's doing is controlling whether our number is negative or positive. So with 60, straight away we can see, well, it's a positive number. This first one's going to be 0. And then kind of figuring out, okay, we're starting from 0. What number can I put in next that won't take me over 60, but it's going to get me the closest to 60. So it's not going to be 64. It will be 32, so I can put a 1 there, so I can plus 32. So a bit easier is if I go 60 minus 32, see what's remaining. It's 28, so I need 28 more, so 16, yes. Put a 1 in 16, so then I have 16. So 12. So now I'm on 40, 48. Need 12 more. So yes, I'll put a 1 on 8. 48 plus 8. What does that give? 56. 56. So it's going to be 4. That's going to take me to 60. The rest can be 0. So my 8-bit binary number is for 60 0 0 1 1 1 1 0 0. Cool. Okay, so why do we use 2's complement over other methods like 1's complement? Other methods like 1's complement, you can have 2 representations of 0, and this can be a bit confusing. So thinking of how do I need to deal with this negative 0. So if we remember 1's complement, all we are doing is flipping the bits. So when we got 0, 0, 0, 0, 0, 0, 0 for 0, we flip all the bits to get 1's complement. This creates us a negative 0 that's just full of 1's. However, in 2's complement, 2's complement avoids this issue with the adding of the 1 bit. So if we have a quick look, in 2's complement, I add the 1, that carries over, I have to carry the 1, add a 1, carry the 1, and so on. This is, when we add all these 1's, it keeps going. We discard any remaining bits that are left over, so anything that goes outside of 8 bits is discarded, and what we're left with is, we're back to just 0 again. So we only ever have one representation of 0. Another reason why 2's complement is chosen, it's really easy to add positive and negative numbers. It's really easy to do arithmetic in 2's complement. So this is a basic example where adding 2 and negative 2, and we can see when you add these two values together, you're left with what you expect, 0. Cool, okay, cool. Thanks guys for watching. If it helped you out, please give me a like, give me a sub, and leave any feedback in the comments. Thank you.